Good afternoon, everyone. I'm Agastya. I just finished my PhD with Peter and working with him now. I'll be talking about the different sources of uncertainty in clean energy calculations which we have, and also describe what we have done so far to control some of them and the ones which we plan to in VECMA. So before I start, I would like to thank Peter, Shunju, Dave, my colleagues whom I've worked with and I've shown results which I've produced with their help. Yuan and Brett are collaborators at Merck. I'll show some results with them. And UCLA Inlux is a foundation who funded my PhD, and a lot of different projects through which I got computational resources to do the work shown here. This is a brief overview of my talk. First of all, I'll briefly go through the rising concern in scientific community about non-reproducible results, not just in clean energy calculation, but in general in any field, both in experiments as well as computational methods, and what are the reasons behind that. Then we'll focus on MD simulations and the method based on MD simulations, and what are the properties of MD which actually cause which arise the uncertainty in the results, even if the initial conditions are kept as similar as possible. And then I'll briefly describe an approach which we use called TIES to control uncertainty in the MD simulation-based clean energy calculations. And then I'll also talk about some enhanced sampling method, which based on parallel sampling. It's a technique which is used to enhance the sampling in MD simulation-based methods. People claim that they can solve the problem of uncertainty. We'll see if it's really true or not. And finally, I'll touch upon other factors which are responsible for non-reproducible results, which we haven't really handled yet, but we plan to do in the VECMA. So, this is a snapshot from a web page on Nature journal. I show this here because to just show that people are really concerned about the non-reproducible results in the scientific community. So this is a special issue which they had a couple of years ago, and they keep updating it, keep writing new articles about it. And you can see they have mentioned something about the non-reproducible results in general. And as Peter was mentioning in the morning, there was like a survey done by Nature. I'll show a video, very short video in the next slide. Before that, this is an excerpt from one of the articles from that issue. And as you can see that here, one of the scientists is saying that we received a call from a lot of people. They could not reproduce our results. So people could not reproduce what they published, and they were not very sure about what the reason was. So this is published. Now this is a very short video. Let's play and then we'll discuss what's there. But this is a survey which Peter was talking about in the morning. It's about a survey done by Nature on about 1,500 scientists, and see what they say.
Is there a reproducibility crisis in science? Nature asked 1,500 researchers this question as part of an online survey. Half agreed there's a significant crisis, and many more identified a slight crisis. Science moves forward through corroboration, when researchers verify others' results. But 70% of researchers who took our survey said they tried and failed to reproduce another group's experiments. And even when trying to reproduce their own work, just over half said they couldn't. Does this mean that most published research is wrong? Our respondents don't think so. Most still trust published results in their field, with physicists and chemists the most confident. There are many reasons why researchers may fail to reproduce results. Sometimes a small difference like shaking or stirring a sample can lead to different outcomes. But the biggest reason, according to our survey, is selective reporting. Things like cherry-picking data to support a pet hypothesis. To get to grips with reproducibility, we need better mentorship, proper use of statistics, and more robust experimental design. All these approaches got ringing endorsements in our survey. Whether it's a crisis or not, right now lots of people are paying attention to reproducibility, That makes it a good time for everyone, funders, publishers, scientists, and the institutions they work for, to act. Read more and delve into the survey data at nature.com/news.
So as you saw, about 70% could not reproduce others' results, and about 50% could not reproduce their own. It does not mean that it's wrong. It just means that we need to be careful about it. We need to quantify and say that this is the confidence interval we have on our thing, and that's the very objective of VECMA. So it's very well placed here. Of course, we don't have error bars on these numbers, 70%, 50%. So I can't say by what confidence interval these numbers are correct, but it is a significant number. So let's move on. There are several reasons which have been identified in different fields why results are not reproducible. For example, for experimentalists, the chemical reagents could be a problem. There was one group which mentioned that they bought the reagent from a different vendor, and there was a different fractional population of different isomers, because of which they could not reproduce their results. There could be subtle things like that. In case of experiments, in case of organisms, it's even more complex. There are so many variables. So the genetic makeup of different organisms is not the same. So you could have a lot of variables in different fields. As in the video they mentioned that cherry-picking data. So you have a confirmation bias, and because of which you might end up trying to confirm what you have in mind, and then just missing out the point sometimes. In case of computational modeling or simulations, there are a lot of assumptions we make sometimes. The theory we use, the model we have, and these simulations are based on a lot of assumptions. The force field which we have is basically fitting to available from the data. So there are a lot of sources of errors possible. Now, these are the different fields and different things. But in this talk, I'll focus basically on MD simulations and more so the free energy method based on MD simulations. So in the next few slides, I have just reproduced some figures from some published papers which show that how much variation we can get using different free energy method based on MD simulations. There are a variety of methods. You don't have to worry about the details of the method, but the point is that there is so much variation. Mind you that the variation you see is using the exact same initial structure, exact same force field and method, and same implementation. This is the first one, which is a method called MMPBSA. It's based on MD simulation. It's an approximate method. You see the different colors. On the y-axis, you have the predicted latency value, the binding affinity value. And you can see that there is a large variation here. It's about, 40 kilojoules per mole. That's even using the same initial structure and same force field. This another method is a variant of the same the method shown in previous slide, again MD-based method called MMPBSA. Again, you can see for 9 different models. This is the HIV model. You can see there is a variation of about 20 kcal per mole or 10 to 20 kcal per mole. Again, a huge variation using the same initial structure. Now, you might argue that the method shown in the previous slide were approximate methods. So let's have a look at the exact method, so-called exact method. So this is a method based on thermodynamic integration, which does not have any assumptions. It's based on statistical mechanics. Even here, you can see that the variation is about 15 kcal per mole. Again, huge. Using the same initial structure, you don't want that. This is another method, which is so-called exact method, getting a delta G actively binding affinity calculation. Again, it's a huge variation. So the point is that no matter what method you use, if it's based on MD simulation, you can see a lot of variation in that, and we want to capture that. Traditionally, people have been running just one MD simulation and giving one number. But imagine if you give one number, it could be anywhere in this range. So does that give you any confidence on the results? Of course not. So then you need. So let's look at why all these methods based on MD simulation. Why do you think? What could be the reason of having such a variation when you have identical initial conditions? So an experiment, what we compare is this experiment. In an experiment, you have a microscopic model, and you have an enormous number of confirmations, and you get a statistical average of that, and you get a number. In MD, what we do is we try to mimic that using a single simulation. So we have not a big model, we just have like a single molecule, and we want to get like a large confirmation set with a large means worth. So you run an MD simulation, you use ergodic hypothesis, and you say on some level is equal to time average, and you run a very long single simulation, and then it will select ensemble of confirmation and get the properties. But then the question is, how long is long enough? There is no answer for that. People have been using it. It has been primarily determined by the computational power you have, and depends on the system as well. So the point is that you can see this paper that it has described the theory behind that. The thing is that all these complex models, they are sort of so-called mixing models, and they are very sensitive to initial conditions. So even if you repeat the method in a different set of initial velocities, it could give different results as we saw in the previous slides. So all the empty simulation methods have this problem. So what we need to do is we need to capture the uncertainty involved in the method, and the way we do it is running an ensemble simulation. Now you don't worry about the details of the method here. The point is that this is the method I was talking about, TIES, thermodynamic integration with enhanced sampling. So in TI, which is thermodynamic integration, it's a method based on statistical mechanics. You need to run, you need to get confirmation sampling at different intermediate points, defined by a parameter called lambda, which goes from 0 to 1, and you can pick up points of different values of lambda between 0 and 1. What we do is, instead of doing a single simulation at each value of lambda, we perform an ensemble of simulations, and that's what TIES does. And if we do that, then it provides us a rule of capturing the uncertainty involved in the methods. To describe you more pictorially, this is a typical TI curve, and we integrate this curve to get the value. At each point, it is like a Gaussian distribution because there is an uncertainty in the prediction. So what we do is we do perform an ensemble simulation at each point, and then get the error at each point, and then perform a stochastic integration, which essentially means that the error in the integration is a combination of errors for all of them. So I won't want to get into more details about it, but that's the gist of what's the way we propose to an ensemble simulation to get a hold on the uncertainty involved in the predictions. Now, as I was mentioning earlier, there are a lot of accelerated sampling techniques which we have proposed. For example, one of them is FET-HPC, which is a parallel tampering or replica exchange method, which is quite popular these days. And people say that you run replica exchange simulation, it might help you get rid of the uncertainty and you can still get away with it. So we thought, let's try that. Let's try running multiple rest calculations and see what we get. Do we get similar results? Do we get different results? So we tried these. Going over that. A lot of data here, but just focus on this particular column. In the bracket, you see the variation in the result we get from 5 different repeats of the exchange. As you can see here, it could go, depending on system, it could vary up to 1.5 in the system we took, but then it could vary even more depending on the system you have. So the point is that even if you do a replica exchange calculation or enhanced sampling technique, you can't still escape or you can't get away by just running one simulation because there is a variation to the data. So the point is that to have a control on error, you need to have ensemble simulation done, and then you can confidently say that this is what my prediction is true within these results. This figure is a pictorial representation of the data shown in the previous slide. What we tried was we extended simulations up to 20 nanoseconds, and we still see that the variation exists. And you see the lines in bold. The prediction, they still vary with time. So even running a long simulation does not help. I will skip these slides and go to the. So far I was mentioning that we take exactly the same initial structure, we take exactly the same force field and same MD codes and implementation. Even then, we see the variation in results. Now, what happens if you change any of those parameters? These are another source of uncertainty, which have not been captured yet, but this is what we intend to do in VECMA. So, if we, there was a recent publication which compared the results, teenage results from different MD codes using the same force field, and they concluded that it is not easy to, they are not portable, it's not easy to get the same result from different MD codes because there are a lot of variations in them, For example, they use different algorithms for the integrators, for pressure and temperature dynamics, different scaling integrators and stuff. Even the choices of physical constants are sometimes different. For example, if you want to use the Coulombic constant or like any constant available number, or this constant which is used in the calculation of energies, they have sometimes different choices and which might affect the results. Then you have soft core functions which is needed for arithmetic calculations, and the way soft core functions are implemented are also different in different amplitudes, which could also lead to more variation. Then you have force constants, bonds, angles, dihedral. These all are the force field parameters, and different force fields have different way of deriving them and different values. So if you use a different force field, of course, you can't expect to get same results. It's another source of variation. Then you have charge and van der Waals parameters. These also vary across force fields. And then if you perform an alchemical calculation, then you need to have a topology file. There are different ways of doing that, some single, dual, hybrid. So there is variation across different amplitudes and different force fields, even in that sense. So there are a lot of sources of variation in free energy calculations which we need to deal with. And partly we use ensemble simulations to deal with the initial conditions variation. But then these are the things we intend to do under VECMA in the near future. So I'd like to conclude with that. But as I mentioned, it's a concern that we have non-reproducible results. We need to work on that. There are several factors which we need to identify and try to account for them while we present our results. In particular, in physical periodic energy predictions, which are based on MD simulations, they have this problem of sensitivity to initial conditions, which is the cause of variation. And ensemble simulation provides a way which can be used. And accelerated sampling techniques also cannot solve the problem. Even then, we need ensemble simulations. Thank you. Great.